Hello guys, I'm Aliva Marcelia from Mechanical Engineering Department, 10 November Institute of Technology, Surabaya, Indonesia. And today I want to explain about powertrain design. And there are three different engines with the wide open throttle performance as below. With the value of A and B of each engine is on the table above. With the rotational engine is about 500 until 6000 rpm, and the vehicle specification is the mass of the vehicle is 1200 kilograms, drag coefficient 0.4, with the row of the air 1.2 kilogram per meter cubic, with the area of the vehicle 2 meter square, with the FR 0.02, with the length of the vehicle 1000 millimeters, and A is the distance from the center of the vehicle to the front wheel is 800 millimeters, and B is the distance from the center of the vehicle to the rear wheel is 1200 millimeters, and the height from the center of the vehicle to the ground is 600 millimeters. And the problem is we have to choose one of these three engines that fulfill the specification considering the price, with the assumption is the price except the engine is neglected, and we have to design the gearbox ratio, and we have to show the vehicle performance curve to exceed the speed of 100 kilometers per hour. And the constraint is the price for the engine with the power of 40 kilowatts is 100 million, and the price is at about 2 millions for the additional of the power every 1 kilowatts, and the 4-speed gearbox ratio is cost 50 millions, and for the additional of the each gear ratio the price is at about 10 million, and the vehicle has the maximum velocity 160 km per hour, and the vehicle can cross the road with a slope of 60 degrees. And the assumption used in this calculation, the wheel radius is 0.3 meters, the addition coefficient is 1.2, the transmission efficiency is 0.8, and driveline efficiency is 0.9, and the final drive ratio is 1:2. And here are the torque and the power of each engine, with the rotation of engine 500 until 6000 rpm, with a step of 100 rpm. And we choose the engine based on the power needed to fulfill the constraint as mentioned before, and the minimum power to run the vehicle is from payload equal to FR times velocity at maximum, and for the minimum power we need about 58.43 kilowatts. And from the engine 1, 2 and 3 there are the torque of engine 1, 2 and 3 is equal about 150 Newton meter, but the maximum power of each engine is different, and for engine 1 the maximum power is 63.18 kilowatts, and for engine 2 is 85.87, and for the engine 3 is 93.06. And based on the minimum power we need, we choose the engine 1 with a power of 63.18, because with this value of power we can fulfill the engine needs for which is 58.3, because considering the price, and the price for the choosing for engine 1 is about 146 million. And now you have to design the gearbox ratio. All the calculation here is based on the book of Vehicle Powertrain System by Mashadi and Kroller. And for the low gear ratio design, we design for the front wheel drive or rear wheel drive for the engine 1 2 3, and this is the normal force of the front wheel, and this is the normal force of the rear wheel. And here are the low gear ratio for if we choose the vehicle for front wheel drive, and this is the gear ratio, low gear ratio if we choose the rear wheel drive. And considering the vehicle can cross the road with slope of 60 degrees, it is better to choose the rear wheel drive because considering the tractive force generated at the rear wheel is bigger, so it is best for us to use the rear wheel drive. And for the low gear ratio, we times the low gear ratio with the correction factor with the value of 1.2, and we got the low gear ratio design for about 6.5. And next is high gear ratio design. To exceed the speed of maximum 160 km/h, from the calculation from book by Mashadi and Kroller, we first find the F star, then P star, and then we can calculate the high gear ratio. And to exceed the speed of 160 km/h and equal to 44.44 meter per second, we had the value of F star is 1183.34 with the power about 52,593.25 watts. For designing high gear ratio transmission, there are three conditions. The first is optimum design, the second is under revving, and the third is over revving. The optimum design is the condition where power load is the power to move the engine, is equal to power engine at its maximum, and under revving condition is when power load is reached at the power of engine at its maximum rotation, and the over revving condition is the condition where payload is reached before or below the power of engine maximum. And for the under revving condition, the preferred is at acceleration, and it is usually used at the racing vehicle. And for the over revving condition, the focus is on the fuel efficiency, and to maintain two of this performance, use the optimum design where the power load is equal at the power maximum of the engine, and at the power generated by the engine at the first slide, we know at the first engine the maximum power of engine 1 is reached at the rotation of the engine at 4,750 rpm. So for the high gear ratio designing, we use the omega optimum at 4,750 rpm, and we got the high gear ratio at the point of 3.35. And for designing the intermediate gear ratio, we just need to know the low gear ratio and high gear ratio, and we design the intermediate gear between them. And for the designing intermediate gear ratio, there are two ways. The first is geometrical and the second is the progressive geometry. And with the geometrical intermediate gear ratio design for the engine 1, we got and in this design we designed the 4-speed gear ratio, and the second gear ratio, the result is 5.22, and the third gear ratio is 4.18. And for the progressive geometry, for engine 1, we get the second gear ratio is 5.22 and the third gear ratio is 3.97. And for designing this transmission, we choose the progressive geometry method for defining the intermediate gear ratio design, because if we're using the progressive geometry design, we can change the engine rotation, so we don't start it at the low rotation, and it has an advantage when the gear wear is equal to each gear, so we choose the progressive geometry design. So from the calculation, we choose the 4-speed gearbox ratio with the first gear ratio is 6.5515 and the second gear ratio is 4.961 and the third gear ratio is 3.977 and the fourth gear ratio is 3.355. And considering the engine price and the gearbox price, which is the engine price is 146 million and the gearbox is 50 million, the total cost needed to build this vehicle is 196 million for about that price. And here is the Simulink powertrain design on MATLAB, where this is the transmission gearbox we design, and this is the resistive force generated, and this is the tractive force generated in the system, and this is the velocity generated the system with the, and we input the properties here, so we can get this performance curve where the engine matching curve, we got this curve, this is the power of the engine, and this is the velocity of the engine, and this is the gear switching curve, and the gear switching is, the gear is switched when the rotational speed is exceed the 6000 rpm. So after each gear reaching the 6000 rpm, it's gear switch, and because we use the progressive geometrical, the low value of after we gear switch it can change. And I'm sorry, and this is the curve to exceed 100 km/h. So from our design to exceed the 100 km/h, we need time for about 13.65 seconds. And when the velocity reach 100 km/h, it traveled for distance for about 240 meters. So this is the vehicle transmission design. So I hope it can be a preference if you want to design a transmission of the vehicle. So see you and thank you for watching.